Hello everyone, and thanks for the interest. Today I'd like to tell you about a new paper by Stephen Tu, Jean-Jacques, Slotine, and I called Non-parametric adaptive control and prediction, theory and randomized algorithms. To understand our contribution, I need to make sure that we're all on the same page in terms of understanding the problem that we're trying to solve. In adaptive control, we're interested in controlling an unknown dynamical system. To make some progress, we typically make an assumption called the matched uncertainty assumption. Under the matched uncertainty assumption, the system consists of a sum of two terms. The first is a nominal stable dynamics, and this dynamics describes the behavior of the system in the absence of the disturbance or the adaptive input. And typically, we assume that under just the nominal dynamics, the system will converge to a desired trajectory. The second term consists of a competition between our adaptive input u and the unknown dynamics d. And critically, we assume that the unknown dynamics lies in the span of the control matrix, which describes how the input enters the system. The name of the game is to come up with an adaptive input that cancels the unknown dynamics and restores the system to the behavior of the nominal stable dynamics. A physical picture you can keep in mind is that of a drone delivery system, where the unknown dynamics represents the changing wind conditions. The nominal stable dynamics represents the performance of the system, for example, in the lab, where it might be the system in feedback with a deep RL policy or an optimal control policy or something like that. And our adaptive input is going to try to learn the changing wind conditions to ensure that the system is restored back to its performance that we saw in the lab. Typically, we assume that there exists a linear expansion of the unknown dynamics in terms of some known basis functions times some unknown parameters. And then to cancel this unknown dynamics, we take our adaptive input to have the same functional form, but times a vector of parameter estimates. When we do this, we make this assumption on D and choose the specific U, then the system is in so-called matched uncertainty form, which consists of the nominal part plus a term that's linear in the parameter estimation error. And then we have to come up with a continuous time algorithm to update the parameter estimates that will ensure this matched uncertainty term is driven to zero. A typical algorithm for this setting is called a Lyapunov-based adaptive algorithm. So if we assume that the nominal dynamics is stable in the sense of Lyapunov with some non-autonomous Lyapunov function that certifies convergence to a desired trajectory x sub d of t, then we can run the following algorithm. We can take the gradient of the Lyapunov function with respect to the state, transform it by pre-multiplication by the transpose of the control matrix and the transpose of the basis functions, and update the parameters according to that. If we do so, a typical guarantee is that in the limit, the system trajectory will converge to the desired trajectory, and we will interpolate the unknown dynamics along the trajectory. And moreover, the state and the parameter estimates remain bounded, so the whole feedback connection of the learning system and the system itself remains stable. Okay, the goal of this talk is to try to relax that linear parameterization assumption. We would like to use approaches from statistical learning theory to search over a more expressive hypothesis class. And in particular, the classical way to get around an assumption of linear parameterization in statistics and machine learning is to go to what is called a reproducing kernel Hilbert space. So let's contrast an RKHS, or reproducing kernel Hilbert space, with standard linear estimation. Standard linear estimation, we search over functions h, such that h of x is given by some basis functions phi of x, inner product with some parameters alpha, where everything here is finite dimensional. The inner product is finite dimensional, the basis functions map to a finite dimensional vector, and the parameters are finite dimensional. In RKHS, we basically go ahead and make all of this infinite dimensional. We replace this finite dimensional inner product by an infinite dimensional inner product in the Hilbert space. Our basis functions now map to elements in the Hilbert space, and our parameters map to elements in the Hilbert space. Sorry, our parameters are elements in the Hilbert space. Now, a priori, this I've actually said nothing about in RKHS. This could just be a Hilbert space, and a priori it's not clear how to do estimation over a space like this. What makes RKHSs very nice is something called the representer theorem, which says that actually this element alpha that plays the role of our parameters, this infinite dimensional element alpha, can actually always be written as a finite dimensional combination of evaluations of the basis functions or the feature map at our data points xi. So we restore to the setting of a finite dimensional estimation problem, but the size of that estimation problem now depends on the size of the data set. Moreover, algorithms for finding these theta I only ever depend on what's called the kernel function, which is given by inner products in the RKHS between evaluations of the feature map, and any function in the space can always be written as a sum of these parameters theta I times evaluations of the kernel. Finally, subject to suitable conditions on a kernel, it defines an RKHS, which can be seen as the closure over all functions that can be represented as finite dimensional linear combinations of the kernel evaluations. Okay, so now to make a connection between the RKHS setting and statistics and what we've been doing so far in adaptive control, I'd like to bring up a slightly different perspective on classical adaptive control algorithms. So we've said so far that our standard adaptive input is going to be the basis functions times the vector of parameter estimates. And we're going to update our parameter estimates according to this Lyapunov-based adaptive law. What I would like to do is I would like to understand what this adaptive input looks like at any given time t. And to do that, I'm just going to go ahead and I'm going to unroll this differential equation describing the evolution of the parameter estimates just by writing formally the parameter estimates as the integral solution to this differential equation. Then I can go ahead and I can plug this expression back into the expression for the input. I can move the y of x inside the integral, and I will find that this standard adaptive law is actually equivalent to a non-parametric form. It makes no reference to any parameters, given by an integral over time of y transpose times some coefficient c of t, where c of t is given by some terms in the algorithm. So importantly, if you look at this, it looks very reminiscent of the RKHS setting because this non-parametric form only depends on inner products between the basis functions y transpose. And in particular, I could go ahead and I could use infinite dimensional basis functions so long as I can efficiently compute these inner products. And that's exactly what we're going to do. We're going to define a kernel input that now lives in an RKHS, which is just given by this non-parametric form where I replace y transpose by this kernel function for a vector-valued RKHS. Okay, so let's think about the complexity of doing so. In a standard adaptive law, I estimate over a finite dimensional space, which is not necessarily so expressive, but what's nice is that the work is order 1 at time t. I just take a single step on this differential equation. In the non-parametric form, I estimate over an infinite dimensional space, which is great, but the work is actually order t at time t. I have to compute this entire integral at every time t, and at time t plus delta t, the integral cannot be simply related to the integral at time t. This is problematic because it means our input gets more and more expensive the longer the system runs for. One way to get around this is to restrict to a space called a random feature space, or F2, where every element in the RKHS is actually formally given by an expectation of some basis functions phi times a sign density that's going to play the role of our finite dimensional parameter estimates, and the expectation is with respect to some known probability measure nu. The reason this space is nice is because I can basically apply the law of large numbers to this expectation, and I can actually approximate any function in the space by an empirical average of the integrand here, where I just draw theta randomly from this probability measure nu. Okay, so now let's give a theory for convergence of the non-parametric input and then understand convergence of its randomized approximation in this random feature space. So let's assume that the disturbance is in a random feature space, and let's look at this non-parametric input that we saw on the previous slide. Then we basically recover all the guarantees from standard finite dimensional estimation. In the limit, we converge to the desired trajectory. In the limit, we interpolate the unknown dynamics, and the state and our function estimate remain bounded at all times. So the feedback connection of the learning system and the dynamical system itself is stable, and we track the desired trajectory. Now, we can use uniform approximation theory to understand how to approximate this kind of optimal non-parametric input by a finite dimensional input in a randomized fashion. And then we can get a high probability guarantee of approximate convergence. So let's again assume that D is in this random feature space. And let's consider the following input. We're going to use a finite dimensional approximation where we have some new basis functions, capital psi, that are a random feature basis, and they come from basically that law of large numbers expression on the previous slide. We're going to update our parameters alpha hat according to a standard adaptive law using this random feature basis. And then we can guarantee that for any tolerance epsilon, if we choose the number of random features to be at least a constant times root n plus root d over epsilon squared, root n plus root d squared, then the system trajectory will always remain bounded, and the lim sup of the norm between the system state and the desired trajectory will be upper bounded by epsilon. So this is essentially an end-to-end bound that tells us how many features we need to track the desired trajectory to an arbitrary tolerance. And importantly, it only depends polynomially on dimension, unlike past guarantees that depend exponentially on dimension because they typically kind of grid the space to do uniform approximation. So let's demonstrate why this polynomial dependence on dimension allows us to scale to high dimensional systems. We're going to look at an m-body system consisting of m particles in d dimensions interacting, say using Newtonian gravitation. That gives us a Hamiltonian in non-dimensionalized units consisting of a kinetic energy term and an attractive interaction. And the dynamics correspond to Hamiltonian dynamics, where q dot is dhdp and p dot is minus dhdq. Our goal is going to be to learn a predictive model of the evolution of this system state. So we're going to assume that the Hamiltonian itself lives in some scalar valued RKHS with kernel k. Then it turns out that we show in the paper, if we define a symplectic matrix that basically just does this kind of gradient rotation that describes the Hamiltonian dynamics, and then we rewrite our dynamics as this kind of rotated gradient where x is the stacked coordinates and momenta, then the dynamics j times the gradient lie in a so-called symplectic RKHS, where the kernel is given by minus j times the Hessian of the scalar valued kernel j transpose. Now what we're going to do is we're going to estimate the Hamiltonian via a random feature approximation in the scalar valued RKHS, and then we'll run an observer-like system that tries to predict the evolution of the system by taking the Hamiltonian dynamics corresponding to the Hamiltonian estimate, and has some feedback term that ensures we stay close to the true system trajectory during learning. And we'll just run a standard adaptive law in this system to try to estimate the Hamiltonian. And if we do this, I'm showing the results here. On the left, I'm showing the trajectory prediction for a 60-dimensional system with 10 particles in 3 dimensions. It's a bit hectic because it's hard to visualize in high dimensions, but we see basically a noisy trajectory at the start that converges to a smooth prediction. If we look at the error in the middle, we see that the error converges to a ball around 0, which is basically the epsilon from our proof, and it's exactly what we would expect. And we also find that the asymptotic prediction error at time t equals 50 decays like a power law of the number of features. Okay, that's all I'd like to say. Thanks for listening. Have a look at the archived version of the paper for greater detail on the theorems and some more results. Bye. Thank you.